Hello boys and girls, so in this video we are going to start our discussion on topic 2, capacitor and dielectrics. We are going to cover 3 subtopics under topic 2, and in this video I'm going to focus on 2.1 capacitance and capacitors in series and parallel. So what is a capacitor? Capacitor is a passive device that is capable of storing electric charges, or in other words, it stores energy in its electric field and returns the energy to the circuit whenever required. So, capacitor might come in different shapes and also size and is used in a variety of electric circuits. Basically, a capacitor consists of 2 conducting plates. These conducting plates is made up of any of the materials such as aluminium, silver or other metals, separate by a small air gap or a thin insulator we call dielectric. For example, we might separate the 2 conducting plates using a paper, glass, ceramics or any other non-conductive materials. The conducting plates could be in the shape of a cylindrical, spherical or parallel plates. But for our discussion in this topic 2, we are going to focus on parallel plates capacitors. This is the symbol for a capacitor in an electrical circuit. Then class, capacitance we denote by capital C. What is capacitance? Capacitance is the measurements of the ability of a capacitor to store charge, or in other words, store energies. So how we define capacitance? Capacitance is defined as the ratio of the charge on either plates of the capacitors to the potential difference between them. So Q represents the magnitude on either plates of the capacitors. V is the potential difference across the 2 plates. Sometimes we might also call the potential difference as voltage. So this is the formula we use to calculate the capacitance. C is Q over V. Capacitance is a scalar quantity. The SI unit is farad, named for microfarads, an English scientist who contribute to the field of electromagnetism. So, 1 farad will be defined as the charge of 1 coulomb stored on each of the conducting plates as a result of a potential difference of 1 volt between the 2 plates. It means that if I have a capacitor with capacitance 1 farad, it means that if I have a capacitor of 1 farad, if I connect it to a power supply of 1 volt, then I will able to store charge of 1 coulomb in the capacitor. Okay, so the capacitance for a capacitor normally does not change unless it is designed to be a variable capacitor. So from equation C equal to Q over V, when we rearrange, we will get Q equal to CV. So we will find out that the charge stored Q is directly proportional to the potential difference across the conducting plates in the capacitors. So a capacitor with a large capacitance can hold more charges than one with a smaller capacitance for the same potential difference applied across them. For example, if I have a capacitor of capacitance 2200 microfarads and I apply to a potential difference of 2 volt, I'll be able to store charge of amount 4400 microcoulomb. If I compare it with the capacitor of 1000 microfarad, if I connect this capacitor also to 2 volt, I'm going to able to store amount of charge of 2000 microcoulomb. So we can see very clearly the capacitor with larger capacitance can hold more charges compared with the smaller capacitance for the same amount of potential difference applied across them. So we can connect all the capacitors either in series or parallel. So let us see what is the main concept when we connect a capacitor in series. So regardless of their capacitance, all capacitors connected in series will contain the charges of same magnitude. It means that the total charge that we saw in the first capacitor will always equal to the total charge we store in the second capacitor when the capacitor connect in series. The total voltage V that we supply to both capacitors connected in series will be shared between the two capacitors. So it means that the voltage V will be V1, the voltage across the first capacitor, plus with the voltage across the second capacitors. So from the equation, Q equal to CV, so V is Q over C. So the total voltage, Q over CE will be Q over C1 plus Q over C2. Since for capacitor connect in series, the charges is same, so we can cancelling the common Q. Then we will get the equation to calculate the total, or we call as effective capacitance for capacitors connect in series. So generally for n numbers of capacitor connected in series, the effective capacitance will be given by 1 over CE equal to 1 over C1 plus 1 over C2 plus until the n capacitors. So this is the formula to find the effective capacitance for capacitors in series. Sometimes we didn't call it as effective, or effective also known as total. Okay, so if you have n numbers of capacitor connected in series, if you want to find the total capacitance, then you can use this equation. We will find out that the value of the effective capacitance will be always smaller than the smallest capacitance in the combinations when they are connected in series. So it will tell us that the series combination will decrease the total capacitance in a in a circuit. So for example, I have four capacitors connected in series, 3 microfarad, 6 microfarad, 12 microfarad and 24 microfarad. So I might calculate the equivalent capacitance by using the above equation. So 1 over CE will be 1 over 3 microfarad plus 1 over 6 microfarad plus 1 over 12 microfarad plus 1 over 24 microfarad. So I will get 1 over CE will be 5 over 8 microfarad. So remember, I want to find for the equivalent or the total capacitance. The total capacitance will be the reciprocal of this equation. So the total capacitance or the effective capacitance will be reciprocal of this value. I will get 8 over 5, or this is equivalent to 1.6 microfarad. So this is how we calculate the total capacitance of the capacitors connect in series. And you will find out that the total capacitance will be smaller than the smallest capacitance in the combination. See, the value will be smaller compared to the smallest capacitance in the combination. Then we might also connect our capacitors in parallel. So for capacitor connect in parallel, they are going to have the same voltage V across their plates. The charges Q1 and Q2 on each capacitor will be different. Why? Because the charges will be separated into two paths. So the charges that we saw in the first capacitor and the second capacitor will be different. So the total charge Q will be Q1 plus Q2. So total Q will be equivalent to the total capacitance multiplied with the total voltage we supply. Q1 will be the capacitance of the first capacitor multiplied with the voltage. Q2 will be the value of the second capacitor multiplied with V. So since the voltage for the capacitor is the same, we can cancel the common V. Then we will get, this is the equation we can use to calculate the total capacitance for two capacitors connected in parallel. So generally for n numbers of capacitors we connect in parallel, the effective or the total capacitance will be C1 plus C2 plus C3 until the n capacitors. So this is the formula to find the effective capacitance for capacitor in parallel. So we will find out that the value of the effective capacitance or the total capacitance will always be larger than the largest individual capacitance in the combinations. Why? Because we total up all the value of capacitance. So the parallel combination normally will increases the total capacitance in the circuit. So if you want to increase the total capacitance in a circuit, then you have to connect all the capacitors in parallel combinations. So let us see one example how we calculate the effective or total capacitance for 4 capacitors connect in parallel. So if I have 4 capacitors connect in parallel, how I find for the total capacitance or the effective capacitance? So it's quite easy. I just total up all the value of the capacitors. So 3 microfarad plus 6 microfarad plus 12 microfarad plus 24 microfarad. Then I'll get the total capacitance or the equivalent capacitance for all these capacitors will be 45 microfarad. So you will notice that the effective capacitance is larger than any other capacitors that we have in the parallel combinations. So next time, remember, if you want to have a smaller capacitance, you connect it in series. You will get smaller C. If you want to get a larger C, larger value of capacitance, then you connect the capacitors in parallel. Okay, clear? Now we move on to the last concept. In this video, we have the energy stored in charged capacitor. We represent by capital U. So class, just now at the beginning of the video, we already say the main functions of capacitor is storing charge, or in other words, it stores energy. So how I'm going to calculate the amount of energy stored in a charged capacitors? So when a capacitor stores charge, it basically stores energy. So if we want to store charge in the capacitor, we have to move the charge from the battery to the plates of the capacitor. So a small amount of work dW is done in order to bring a small amount of charges dQ from the battery to the capacitors. Okay, in order to store the charge in the capacitor, I repeat, in order to store the charge in the capacitor, we have to move the electron from the battery and put it in the plate of the capacitors. So, and in order to do this, we need to do work. So the work done to bring a small amount of charge from the battery to the capacitor is V dq. And how we find V? V is Q over C. Come from the definitions. This one is come from the definition. C is Q over V. So we rearrange, we get V is Q over C. So I put it in, so the amount of work we need to done will be Q over C dq. So this is a small amount of work in order to bring a charge to store in the capacitors. So the total work done, W, need to increase the capacitor charge from 0 to a final value Q will be given by the integration of Q over C dq from 0 value to the final value Q. So class, how we do the integration? So the value of capacitance is constant, so we no need to integrate the value of capacitance. So we are going to integrate the value of charge Q dq. So integrate Q, we will get 1 over 2 Q squared. So we have this one. The work done to accumulate the charge in the capacitor to a final value of Q will be given by half Q squared over C. So the work done to charge the capacitor W will appear as the electric potential energy U stored in the capacitor. So the energy stored in the capacitor U actually is equivalent to W. So we have U equal to half Q squared over C. So this is the equation to determine the energy stored in capacitors. And now we know that C is Q over V. So I substitute C with Q over V. Then I simplify, I will get U is half QV. So this is the second equation that we might use to calculate the energy stored in capacitors. Then class, we also know that Q is CV. So I substitute the Q with CV. So I'll get the third equations used to calculate the energy stored in the capacitor. We have U is half CV squared. Which of the equation we are going to use to determine the energy stored in the capacitors? It depends on the information provided. If you know about the charge and the capacitance, you might use the first equation. If you know about the charge and the voltage supplied to a capacitors, you might use the second equations. If you know about the capacitance and the voltage of the capacitors, then you might use the third equations. So what is the unit for energy? What is the unit for energy? Yeah, as we have learned before this, unit for energy for sure is joule. Okay, so the energy stored in the capacitor, the SI unit is joule. So class, we have come to the end of this video. So we have done with all the concept in 2.1. We have capacitance and capacitor connect in series and parallel, and the energy stored in the capacitors. So you might try to attempt tutorial 2, question 1 and question 4 that related to all the concept we have discussed so far in this video before you enter the tutorial class. Then I shall see you in the next video about 2.2, whereby we have charging and discharging of the capacitors. Thank you for your focus. I'll see you on the next video.